Okay, so let me repeat my request that more of you will turn on their video. It really makes a difference for me, so please do that. Thank you. The topic today is dynamic programming. We saw in the prior class one example, just to remind you. The example was the problem of longest common subsequence, where you get two sequences, X and Y, and you would like to find the longest subsequence, which is common to both. And the observations there was that the length of the common subsequence, if you look at the prefix of the two sequences, so this is sequence Y, this is sequence X, and you can at any point in this array represents the longest subsequence up to this point for the two prefixes that end here. So, for example, if we look at this point, for example, this prefix from here is of 3 elements. The prefix from here is also of 3 elements. And the fact that you have 2 here means that the longest subsequence between these two prefixes has 2 elements. The observation back then was that the way to figure out the LCS, the longest common subsequence of a given point here, depends on basically on 3 entries of prior prefixes. Either this one, which means that if we have 3 elements on the Y and 3 elements on the X, this one means 2 elements on the X and 3 on the Y, or this entry right here, which means 2 elements on the Y and 3 on the X, or this entry, which means 2 on the X and 2 on the Y, and then comparing the last character C to C, and since it's the same, we can take this value and add 1 to it. The big picture here is the following, and that's the big picture of dynamic programming, is that you are unready when you start filling up the table. You really have no clue how to advance. So instead of that, you advance in all directions, you fill all the values, and when you reach the value of interest, in this case, it's the comparison, the full comparison of X and Y, which means the full prefix, which means the whole thing of X and the full Y. At this point, you draw the value, which in this case was 4, the length of the longest subsequence, from these 3 entries, above, to the left, and upper left. And but you have no idea where you will draw it from until you get there. So keeping all the options in the air, but still not in an exponential form, but under control, in some polynomial fashion, is what dynamic programming is all about. Because if you think about it, the number of possible subsequences is really exponential. But this allows us to keep under control the frontier, which is the diagonal going this way, which means that the maximum size of the frontier is linear, and therefore the complexity is kept under control, and in this case it was n squared. So we are going now to advance to the second example of dynamic programming. And the second example has to do with the problem of matrix chain multiplication. So what is the problem? The problem is that you are given n matrices, A1 up to AN, and you need to compute their product, A1 times A2 times A3, till AN. Now, why is this an interesting problem? It is interesting because the challenge is to come up with the correct order of parentheses, because how do you multiply two matrices? You basically need to do, and that's our assumption, as many operations as the dimensions of the first matrix, meaning n1 times n2, and then n2 got to be the first dimension of the second matrix, so it will be n1 times n2 times n3. Now, clearly, when you start multiplying matrices, what goes away when you multiply two matrices is the shared dimension, right? Because if I multiply A1 times A2, the product will be N1 times N3. So the second dimension disappeared. Is that clear? And since it disappeared, this can be a prime target to get rid of early, because if we were to keep including this huge dimension in all multiplication going forward, we will be repeatedly penalized with this high dimension. Okay, so that's really part of the philosophy, but this is not good enough because that sounds like a greedy approach. As we are going to see, we will need the full, we need to keep track of the various parenthesization of smaller things, because we are going to look at it recursively, and only by keeping track of all the different prior possibilities, we'll be able to figure out the optimal next step. So basically, the formula that is going to guide us will be the following. I and J are two matrices, somewhere between 1 and n. So give me a sub-interval, if you will, that ranges between matrix AI and matrix AJ. In the beginning, A1 is I equals J, so there is nothing to do. And then, of course, you need to keep increasing the intervals. Okay. So if I'm looking for the best way to multiply the matrices in this interval, AI up to AJ, what will be the correct recursion to think about it? I could break at any k, so the assumption here is that J is larger than I. I could break at any k in this range, right? As long as k is larger than equal I and less than J. And I could ask myself recursively, what is the best value for multiplying the matrices between I and k, and between k plus 1 and J? And then what will I need? I will need to still multiply the matrix that came out of this prior multiplication, which is the matrix whose dimensions will be the first dimension of this matrix, of matrix AI, the second dimension of the matrix AK, the first dimension of the matrix, I'm sorry, I'm not looking at the right place. The first dimension of the matrix AI, the second dimension of the matrix AK, and the second dimension of the matrix AJ. So this is what will remain to be done, assuming that I've done in the optimal way the matrices from I to k and from k plus 1 and from k to j. Does this recursion make sense to everybody? Okay. So if it makes sense, let us try and understand what it actually is telling us. It is telling us that where would be the starting point, you know, or where will be the termination condition of the recursion. Whenever there is a recursion, there is a point where I don't need to compute anything because that's a starting point. It's like the recursion when you go to 0 or to 1, when it's clear what you don't call any more recursions. So the observation here is that if I equals j, meaning I have a single matrix, I have nothing to do, right? So obviously the number of operations I need to do for that is 0, okay? And then to look at increasing difference, and here I apologize for using the letter k twice. Here k meant the value where I break. Here k means something else. It means the gap, the j minus I. So here is the game plan. The game plan will be to start with a k, a difference of k, which is 0, because there I have nothing to do, and then keep increasing the k. The k is the difference, is the size of the interval. So at the beginning, I only consider single matrices. Then I will consider successive pairs of matrices where I really have no choice, you know, because if I'm to multiply a matrix A1 by A2, I have only one way of doing that, or A2 by A3. So this will be a k of 1. A k of 1 is really boring. But when I reach already a k of 2, I have an issue here of whether to multiply the first 2 matrices and then the third, or the second 2 matrices and then the first. Okay, so I start having choices. And what we see here is the example of k equals 3, meaning 4 minus 1 will be 3. So we have 4 matrices that we need to multiply, or 3 matrix multiplication. So what are our options? Our options is to first multiply the last 2, then the second multiplied by then, and then the first multiplied by the product. Second possibility, multiply the A2 and A3, then multiply by A4, and finally A1 times the product. Third possibility, A1 times A2, also A3 times A4, and now multiply the 2 products. Fourth possibility, multiply A2 by A3, multiply A1 by the product, and then the product times A4. And the last possibility is A1 times A2 first, multiplied by A3, and then by A4, which is just the normal left to right multiplication. Okay. So what I'm trying to tell you here is that these 5 options are all represented in this recursion. So how are they represented in this recursion? I can take the last multiplication as the pivot, and then ask about the other things. I defer them to these recursions. So this is my recursion I to j, 1 to 4, right? So I can take any k in between, and the k can be 1, 2, or 3. Okay, so let's see how these options are represented in the prior formula. In the prior formula, this will be K equals 1, because the last multiplication will be A1 times something, right? And observe that here also A1 will be the last to come in. So K in both cases will be 1. What will be the difference? How will I take into account the difference between the first option and the second option? It will come through M24. Right? The M24 will account for these two possibilities. Either do first the multiplication of A3 and A4 and then multiply by A1, or first A2 and A3 and then A4. This case will be captured by the K, where K is 2, because I split in the middle, and then I really have no choice. If I split in the middle, I have just two matrices before and after. So that's a boring case. And here, K equals 3, and where K equals 3, what will go into the equation is M44 and M13. M13 will actually break into two cases, this case and this case. But for this top part of the recursion, this is what I see. Okay, so after having this high-level discussion, and before going to reasoning about the complexity, I wanted now to show you how you fill up this the table, the dynamic programming table, which, if you remember, I explained in the prior class that the programming here meant programming people as opposed to programming by computer. So what you can imagine here is an army of human beings starting to fill up methodically this matrix right here on the left, and they all contribute to the computation. Okay, so let's see what's going on here. So the example that we consider here is this example, where A1 is 30 times 35, and that's the dimension. A2, the dimension are 35 by 15. A3 is 15 by 5. A4 is 5 by 10. A5, 10 by 20, and 10 by 25. Now, let's try and second guess, because it's always good when you look at a numeric example, try and second guess what would be a good strategy. So what is so I'm doing that just to give you some intuition, because, you know, I can go and do a simple drill, just go and plug in the recursion and leave it at that. But I think it's really interesting to try and reason about the problem ourselves, make sense of it, and then look at what dynamic programming gives us. So let's apply just our common sense. We have this total of 7 dimensions, right? 30, 35, 15, 5, 10. So obviously, what is the smallest dimension here? It's 5, right? So what will be my best deal? My best deal is to include as many multiplications as possible where 5 is one of the dimensions. Is that clear? So, not surprisingly, if you look at this table, and I'm going to come back to it later, you see that where to split, you see the number 3 all over the place. 3 is the dimension of, is the second dimension of A3. So we are going to see the meaning of this number, but what it actually is telling me is that in all these optimal multiplications, the place to split is around 5. So 5 will be a repeated dimension in the solution that we are going to derive using dynamic programming. Okay, so I don't expect you to fully understand this here, because I'm yet to present the full dynamic programming dimension. I'm just trying to build a bridge to your intuition so you will appreciate what's going on and why it meets your intuition. Okay, so I hope that I made this point clear, that in this example, 5 is by far the most attractive dimension. And the more times it will appear in the recursive matrix multiplication, the better we will do. Okay, so now let's try and see why this is a proper a way to unfold the recursion and actually fill up the recursion after we unfold it from bottom up. So what do we see here? We see here, as you remember, we go from I to j. I is the smaller number. So we put the first dimension of I here, 1, 2, 3, 4, 5, 6. So these are this is where we start. That's the first matrix. And the second matrix, the horizon will be j. So j is written here in the reverse order, 6 up to 1. So this node up at the top means that I start at matrix 1 and I end at matrix 6, which is really the product of the 6 matrices. This is captured here. This is the smallest number of operations that as implied by the dynamic programming solution that I'm going to present. Okay, so is it clear to everybody what every rubric here stands for? So for example, this rubric gives me the best, it tells me that 7125 is the smallest number of multiplications for multiplying matrices 2 through 5, meaning A2 up to A times A3 times A4 times A5, because 2 is the I and 5 is the J. Okay, so now let's see how we start filling up the matrix. Remember the base case. Base case is I equals J, right? So I have just one matrix, I have nothing to do. This is written in this row, because in this row we have, this 0 means matrix A1. This, because it's 1 here and 1 here. This location means matrix 2, 2 from J, 2 from I and 2 from J. This means matrix 3, which is 0, just the matrix as is. Matrix 4, matrix 5, matrix 6. Is that clear? So that's the meaning of this row. What's going on in the next row? In the next row, it's really a no-brainer because what it's telling me, this location is 1 on the I and 2 on the J, which means no choice, just multiply matrix A1 by matrix A2. Right? There is no decision point here. So what will be the total number of operations to multiply them? So we have to look at the dimensions. It will be 30 times 35 times 15. And you can convince yourself easily that this is the correct number because 30 times 35 is about 1,000 times 15, it's about 15,000. So it looks right. Okay? What is this? This is A2 times A3. 35 by 15 times 5. Again, that's the correct number. This is A3 times A4. So 15 times 5 times times 10, right? Yeah, so 15 times 5 is 75, times 10, 750, okay? Then we have 5 times 10, 50 times 20, 1,000. 50 times 20, 1,000. Then we have 10 times 20, 200 times 25, 5,000. Okay? So we filled this up completely boring because what it actually told me, just take, you have two matrices, you have no choice, multiply them, nothing. So the first row here, where we start having some intelligence, is right here. Okay, so let's see what's going on in this location. Here we are going to account for multiplying the best way to multiply A1 times A2 times A3. So what are really our options? Our options are to multiply first A1 times A2 and then A3. The fact that the number here is smaller than the number here tells me that I didn't go through this route, right? So let's select what, if I can really get the other alternative. So this gave me a huge number, obviously. It should have been larger than this, so no point of it. So we need only to convince ourselves that we had this option. So what was the other option? The other option was to multiply first A2 times A3, and now how much we need to add to it? We need to add to it 30 times 35 times 5, right? You see why? Because I already multiplied A2 times A3, so I'm now I overcame the 15. So now 30 times 35 times 5 is about 5,000. Add 5,000 to this, you get that this is a correct number. I mean, it sounds correct, and you know, we can take a calculator and figure that out. But you see how we reach this number? We reach this number by first doing A2 times A3 and then multiply A1 by it. I just demonstrated to you that we could get this number this way. Same here. Here, what were our options? Our were either to come from here or to come from here. And from what you see from this table is that whenever we had an option of splitting around 5, we always preferred it. The only time where we didn't have such an option was here or here, and we didn't do it, but everywhere else we use this as a split. So now what I'm going to demonstrate to you, let's assume that this is filled up correctly, okay? And the cases that we are going to discuss here are the cases where we need to figure out M2 to 5, meaning what are my options of multiplying matrix A2 times A3 times A4 times A5. Okay, so these are the 3 options that we are going to consider. And what I need to convince you is that based on whatever I had prior in these 2 rows, let's call it this row and this row, which is computed prior, that the best result I could give you is the 7125. So I'm going to assume that the numbers here and here are correct, okay? And I'm going to try and convince you that 7125 would be what I will conclude after filling up these 2 rows. So what do I need to compute? I need to compute M25, right? Starting at matrix A2, multiplying by A3, by A4, by A5. How to best compute this product of 4 matrices. So what are my options? Option 1 is to first figure out the best way to compute A3 up to A5, and then multiply matrix A2 by them. So what will be the cost of doing that? The cost of doing that will be to compute 3 to 5, which is 2,500, right? And then, this is where I will take the value for this. It's written, it's already computed for me. And now I need to compute the 3 dimensions that remain. So what are the 3 dimensions? It will be 35, which will be the first dimension of A2. 15, which is the second dimension of A2, and 12, the second dimension, 5. This will be a pretty famous number, right? Because it will be 35 times 15, which is give or take 500 times 20, which is, you know, by my approximation, it would be so it will be a pretty large number, and for that reason we end up with 13,000, which is too high. As we see, we can get a better number. Second option is to split after 3, which means that we multiply A2 by A3. We also multiply prior A4 by A5, and then multiply the remaining matrices, which is the product of this and the product of this. In this case, what will be M23? M23 is written here. M45 is written here. And what remains to be done is multiply 35, which is the first dimension of A1, 5, which is the second dimension of A3. Remember that this is a very attractive number, and for that reason, we always keep it in. We try to use as many multiplications with 5 as possible, and then 20. So this number comes out as really modest. 35 times 5 is, say, about 500 times 20, and this will give me the total of 7120. And the last thing that we need to consider is the possibility of breaking after A4, which will be M25 plus M55, which this is of course 0. This M24 is M24 is written right here, and then we have this slash multiplication, which will give me a bigger number. So what I hope I demonstrated is that this number 7125 became possible as a result of assuming that all of this is correct, and we choose it because it's the smallest number. Okay. And I hope that it is also clear how the minimum upon filling up each of these rubrics gives me the point to split, because that's the last thing that we need to do, and the rest is captured by the recursion. So is it clear to everybody why the minimum here tells me where to split, which is really the operational side of this computation? So go ahead.
Yeah, just to confirm, the P1s are P are the product of the matrices, right?
What?
Like P1, P3, P5. So these are the product of second element, like A1's second dimension.
Yeah. So the PIs are the dimensions.
So these are the second dimension or the first dimension, like
second.
for second.
The second of the first matrix.
Second of the first.
Because this is the joint dimension with the second matrix to multiply. You always multiply two matrices, right?
Yeah.
So it's the second dimension of the first and the first dimension of the second.
Okay. Thank you.
Okay. Sorry. So this is really the dynamic programming solution, and the only thing that remains to be reasoned about, unless you have any questions about it, is what is the complexity. So I'm going to try and explain why the complexity is on the order of n cubed. So where do you see the n cube hitting us? So let's think about it. Where I look at these operations, when I'm very low, just, give me at this level, no choice. So it's, here I just do matrix. So it's not the matrix multiplication, of course, complexity. It's the complexity of figuring out the dynamic programming, okay? So here, basically, it's a very, I hardly have to compute anything. It's just straightforward. So you can say that this is n, if you will. When I'm at the top, the very last recursion is also linear in the number of matrices. Why is that? Because let's look at what we are doing there. You need to consider, so if you give me, if this is 1 and this is 6, I need to consider 6 different options, right? Or 5 different options. That's all. So what I'm trying to tell you is that when I'm very low here, or even level above here, I still need to do more or less a linear number of operations, and here also a linear number of operations. So this would have lent itself to n squared. So where is the n cube coming from? Is it clear what I just said? Here, for this given point, I need a linear number of choices. So 1, 6, I will need to make a choice between 5 or 6 options. Take the minimum. Here, for say this level where I start needing to make a choice, each point I need to make a choice between 2. And suppose I have m options, m different entries here, so it will again be linear. So where is the m cube coming from? Because if it's linear at every row, what I have so far is m squared, not m cubed. So here's the answer. The answer is, I try to capture it by imposing this image. So imagine that this is a small, a miniature image of this triangle. So just think about it as capturing this triangle by a miniature image. So what I'm going to do, I'm going to limit my attention sub-area in this triangle. And what is the sub-area? I'm going to look, so if this is n or m, if you will, then I'm going to look at the area which is between, if this is 1 and this is n, I'm going to look at the area between 1/4 of n and 3/4 of n. Okay, so here I'll have about half n between them. So if you try to let your imagination go and imagine that we have here n, that this is really big. It's not 6, but a huge number. Then I look at the, I remove the top quarter and the bottom quarter, and I remain with half of the rows in the middle. Okay, the value of that will become clear soon. So that's exactly what this image has to convey. Now, what is the point? The point here is that when I'm in this middle and you give me the case that I need to consider, all the gaps, how many gaps will I have? The answer is that I will have order of n gaps. And for each of these gaps, how many values will I need to compute? Order of n. So each of these rows in this space, and I have a total of n over 2 rows, will require n square walk. And for that reason, the total complexity will need to be on the order of n squared. So it will be some constant times n squared, but the constant may be lower than 1. But that's the reason. Because the amount of work in the middle is much higher than in the extreme. At the top, things starts converging. At the top, things start converging, and here there is little work to do at the bottom. Okay, so this is it. If you have questions about it, that's the time to ask. Otherwise, we can move to the next, move on to the next chapter. Okay, so just a few words before I move to the next chapter. I follow the order of the book, which is not, you know, you could argue for the opposite order, because the next chapter, and I'm going to soon post the slides for that, is surprisingly for a family of easier algorithms. Unlike the situation with dynamic programming, we are going to discuss a situation that can be addressed by greedy algorithms. And dynamic programming is captures a situation where you need to keep all the balls in the air. And only at the very end, you figure out which of the different things that you kept gave you the best solution. In greedy algorithms, situation is much easier. You can start building the solution as you go. And you can commit. Here you cannot really commit to anything until you finish the evaluation, and then you can choose the winner, as we saw. So going now to switch to the second to the next group of slides. Let's see. No, it's not that. Sorry. I'm sorry. Just a second. Let me see if I have it open. Yeah, I have it open. Okay. For some reason it didn't show. Yeah, okay. Okay. So we are moving now to chapter 16. Chapter 16, the title is Greedy Algorithm, and the basic paradigm can be captured in one sentence. Choose what looks best now. So you're given a bunch of options, you need to solve a problem. Be greedy, go for what looks to you best. It will be best overall. Okay, so we are going to demonstrate greedy algorithms on two examples. First example, the following. Consider a lecture hall that needs to be allocated to lectures. And the rule is that only one lecture can take place there at a time. And we are talking about allocating it to a bunch of lectures during a day. And our objective is to allocate it to the largest number of lectures. So what are we given for each lecture? For each lecture, we are given its starting time and finish time. So in this case, lecture 1 starts at 1 o'clock, ends at 4. Lecture 2 starts at 3, ends at 5. Lectures 3 starts at time 0, ends at 6, and so on. Okay. So for each lecture, we are given start time and end time, and the assumption is that they run continuously. So they start and end, and they need the lecture all throughout. Okay. What is the objective? The objective is how to fit the largest number of lectures into the lecture. So how are we going to solve it? So the first step, which is already shown here as if it was already done, but you should not be confused by the fact that it is already done for you, is that we take all the lectures and we sort them by their finish time. Okay? So observe that the finish times are increasing as you go up. Okay? But this didn't happen by coincidence. It's really the first step in the algorithm. Okay, so suppose we did the sorting, and now comes the algorithm. And the algorithm is really a one-liner. Once we have done the sorting, is pick the earliest finish time and repeat. Okay. So let's see what is this solution telling us to do, because it requires some more detail. Okay, so what is the first finish time as we start going? So we sorted it by finish time. So obviously the earliest finish time in the beginning is 4, right? Because we sorted it by finish times. Now, the fact that, so I pick this lecture and I commit it to the whole. That's what greedy is all about. What do I do next? So clearly I do not proceed immediately to pick the second lecture, but instead I start going through the lectures and I start chopping off all those lectures that overlap, because clearly by committing to a lecture that starts at 1 and ends at 4, I made a clear decision not to take the lecture that starts at 3 and ends at 5 because it overlaps. I also made a decision not to include the lecture that starts at 0 and ends at 6 because it overlaps. Okay, so I go through the lectures and I keep throwing out anything that overlaps the lecture I already committed. So what this means is that you shouldn't read too simplistically this one-line algorithm of pick the earliest finish time and repeat, because it has the side effect of getting rid of some lectures, which is not written here. What is the next lecture I will pick? It is lecture 4, right? Because lecture 4 is the earliest one in terms of finish time when I go through this order, and it's the first one that doesn't overlap. So I pick lecture 4 that goes from 5 to 7. And then I start going through the remaining lectures, 3 to 9, overlaps, out. 5 to 9, overlaps, out. 6 to 10, overlaps, out. And now I reach 8 to 11. 8 to 11 doesn't overlap 5 to 7, right? So I pick this. And then I start taking out 8 to 12, 2 to 14 because they overlap. And finally, I pick 12 to 16. Okay? So this is the algorithm. So do you get the point of why is it called greedy? Because indeed, I do the sorting, which is in a first stage. But once I do the sorting, whenever I start going serially through my options, I'm ready to make a decision and never regret it, never go back. And this is the characterization of greedy. Well, you have a choice, and the choice is partial, meaning by picking the first lecture, I definitely have not committed to anything else. The only thing I can tell you is that it's going to be in my solution. I'm yet to consider other things. If you ask me who else will be in your solution. Okay, so do you see why why greedy is the correct characterization of this paradigm? So now, as always, we have these two questions that we can ask. Is it correct, and what is the complexity? So, is it correct? How are we going to argue about correctness? So, anybody wants to give it a try? This slide actually gives you the overview of the correctness proof, but if anybody wants to give it a try to actually demonstrate how to apply what's written here, or if you have another solution, fine. So what is my claim? What is the correctness claim? The correctness claim is that I solve the problem, meaning that this algorithm gives you or fits the largest number of lectures into the lecture. Right? This is the correctness claim, that you have no way for this data to give me, or for any input you will give to this problem, you have no way of fitting more lectures than what this will give. Okay, this is clearly the correctness claim, right? Because this was my problem definition. Okay, so if you accept that this is the correctness claim, the question is, how am I going to argue it? And here you have the basic idea. The basic idea is that you come to me and say, oh, what you're talking is complete nonsense. Here is a better solution. Okay. But I'm going now to argue that no matter what alternative solution you give me, it will never have more lectures than what this algorithm gives. Okay? And if I do that, it's clearly a proof of correctness. So what will I ask you? I will ask you, when you give me your hypothetical alternative solution, or you challenge me with your challenging solution, you challenge me with a solution, I ask you, does your solution have or does not have the first lecture that I chose, the one in this example that goes from 1 to 4. If your solution has this lecture as well, let's omit it from both and proceed. Let's omit it and everything that overlaps it and apply this consideration again. So for the sake of correctness or proof of correctness, this will be only interesting if we hit some lecture that you have and I don't have, right? Because you claim to have more lectures. So certainly you should have such a lecture that you have and I don't have. So let's make, without loss of generality, the assumption that already the first lecture you don't have, you have something else. So here is how I'm going to argue. I'm going to try and add my first lecture to your choice. If I can add it without throwing anything out of your choice, what does it mean? That your solution was not optimal, I was able to increase it. Okay, so this contradicts your claim that your solution is optimal. Now, if my first lecture overlaps one of your lectures, what I'm going to do, I'm going to replace it in your solution. Clearly, by doing that, I'm not going to hurt any lectures that you chose because my lecture is the one with the first finish time. So if your lecture contradicted any lecture and had to rule them out, our replacement will not hit more lectures than you already hit. And that's basically the inductive process here. I will continue to replace each and every lecture you gave me by my lecture, my corresponding lecture, first the first, and the second, and the third, and so on. And at the end, I will argue that you could not have yet any other lecture. Because if you could have more lectures, I could add it to my solution. So do you see here the combination of arguing by contradiction and doing it in an inductive process? So you see here, it's a form of an inductive, of proof by contradiction combined with induction. Questions about this reasoning about the correctness proof? Okay, so this is the correctness proof. And in terms of complexity, what we really do here is, of course, we need to account for the sorting, but, and you know, whether you can do this sorting in n log n or in linear time, you know, if these are integers, maybe, doesn't matter. Point is that sorting is not the interesting part in this solution. What is interesting is the greedy part, and in this case, it should be obvious that it's done in linear time. Any questions about this simple example of a greedy algorithm?
By finishing by picking up the earliest finish time, you mean the shortest lecture, right?
No.
So what does that mean?
Like every lecture has a time. So every lecture request, I want the whole from 1 o'clock to 4 o'clock, 3 o'clock to 5 o'clock.
Okay.
So finish time is the time.
Okay. Okay.
No, so this has nothing to do with the length of the lecture.
Got it.
What you're saying is It's not an unreasonable heuristics, but you will not be able to prove that it gives you the smallest number. Okay? I can give you a trivially counter example to what you say. Just imagine that I have a lecture that takes 2 hours, say from 5 to 7, okay? And suppose that all lectures either end at 6 or start at 6. If you give me this 5 to 7 lecture, I knocked out everything else.
Hmm.
Well, I could clearly fit 2 lectures that could be much longer.
Hmm.
Okay?
Yeah. All right.
Okay? Other questions about this solution? Or this paradigm? What I really care to convey here is a paradigm, and in a way, the reason that this is so important is that whenever you need to solve a problem, come up with an algorithm for a problem, always you need to ask, can I find a greedy algorithm? Because it will be an embarrassment if there is a greedy algorithm and you do something more complex. Okay. Clearly, if you can do a greedy algorithm, there is no reason whatsoever to do something more involved. So in a way, greedy should be always your first choice. And you need to convince yourself, in fact, given a problem, that you cannot solve it in a greedy fashion. So greedy is really the square one, because it's the simplest. And in a way, it's funny that the book chose to put it in chapter 16, I'm sorry, after having us consider more involved thought. But maybe it makes sense because you can appreciate greedy only after seeing that it didn't work in other cases. Because you present greedy too early, will not appreciate the thinking you need to do in order to figure out whether greedy applies or not. Okay. Is it okay to proceed to the next example? Okay. Next example is something that definitely the electrical engineers in the audience will be aware of. It is it's known as the Huffman code, and I'm going to define for you the problem. So the problem is what's called binary prefix code. So what does it mean? It means that I have a data file with, say, 100,000 characters. So a character may be the letter A, the letter B, the letter C, so in this example written here, we assume that we have an alphabet of 6 letters, A up to F. Okay? And we are allowed to use a binary code to represent every letter, each letter, and the question is how to best represent them. So clearly, if I have 6 letters in my alphabet and I'm limited to binary codes, what is the smallest number of bits I must use in order to represent them? So clearly, 1 bit will not be enough because 1 bit will allow me to only represent an alphabet of 2 letters. 2 bits will not be enough because they allow only 4 different characters. 3 bits will be enough because they allow me up to 8 different characters. Okay? So it should be clear that I need at least 3 bits for the code. But now I have really 2 different approaches. One approach is just the dumb approach. I need 3 bits. Let's attach these 3 bits, 3-bit codes arbitrarily to the 6 letters. And this is what's written here. A will be 000, B 001, and F will be 101. Okay? And clearly each of them is different. Each has the same number of code words, and problem solved. But the question is, what I would like is to take this 100-character data file, so it comes as a string, and I would like to use the smallest number of bits to represent it. Okay. So clearly, if I have 100,000 characters, and you give me these codes, what will be the total length of the code? It will be 300,000, right? Bits. If I use fixed length, right? And the question is, can I do better? And the answer to that is this idea of binary prefix codes. So binary prefix codes means that I am going to use codes, and now I'm not limited to just 3 bits, such that no code word will be the prefix of another. That's why it's called binary prefix code. So in this example, suppose that this is my binary prefix code. Observe that if you give me a string, and if the first character is, so suppose that this is my binary prefix code. If the first character is 0, I don't need to look further. I know it's an A, right? And then I can look at the next character. If the first character is 1, I look at the second. If it is a 0, I look at the third. And if the third is 1, I know it's a B. If the third is a 0, I know it's a C. Okay. Now, but if I look at the first character, it's a 1, and the second is a 1, I need to look further. If the third is a 1, it's a D. But if the third is a 0, I need to look further. If the fourth is 1, it's an E, and if the fourth is 0, it's an F. So what you observe here is that if you look at these codes, none of them is a prefix of the other. Meaning 0 is not a prefix of this 5. 101 is not a prefix of this 4, or A, of course, or of 0. 100 is not a prefix of this. 111 is not a prefix of this. And 1101 is not a prefix of this, and etc. So, okay? So that's the basic idea. And of course, the whole importance here is only if it gives us a better deal on the overall length. So what will be the basic idea here and the justification right off the bat before we go deeper into the algorithm of using variable length code. So the assumption is that we know that the frequency of the different characters that I want to encode is very different. Like in this case, suppose I have a total of 100,000 characters and A appears 45,000 of the time, B 13,000, C 12,000, D 16, 9, E 9,000, and F 5,000. So what you see here is that we really have these three groups. This appears more than others, so it has a single bit. These three has a medium frequency, and each has 3 bits. And these two has the lowest frequency, and they have 4 bits. So the overall reasoning here is that the big gain will be here, because we switched from 3 to 1, and the penalty will be here. And you can immediately see that that's a gain. How can you see that this is a gain in overall length? Because for fixed length, what was the total number of bits? It was 300,000, right? So now let's see what's going on. When I hit a B, C, or D, both codes have 3 bits. No difference, right? But for E and F, I pay a penalty of 1. Here I had 3 bits, here I have 4. Here I had 3, here I have 4. And my gain is here. How many times A appears? 45,000. How many times E or F appear? 14,000, right? 9 plus 5. So 45 minus 14, which is 31,000, will be the number of bits that I save by going from this code to this code. Is that clear? Does this make sense? So this is a demonstration that binary prefix codes have value. But is what I demonstrated to you the best I could do using binary prefix codes? The answer is going to be given through a greedy algorithm that we are going to consider in the next class. Okay, and this is known as the Huffman's algorithm. We are going to reason about its complexity. So I'm going to present the algorithm, reason about its complexity and correctness, of course. Okay. So any questions? Okay, so I'll see you Monday. There are no questions. Okay, bye-bye.